All right, we want to chat quick about particle tracks and particle accelerators today. And this is setting us up for our very last lesson, which will be Monday, in terms of how we found these things. We want to talk about elementary particles, and we've kind of talked down to the level of the nucleus, and now we're going to go structure the nucleons themselves. By 1932, we knew about 4 different elementary particles. We had electrons, we had protons, we had neutrons, we had neutrinos, we had positron, which is the antiparticle of the electron, and then, of course, the photon of EMR. And these were thought to be elementary, as in you couldn't get smaller than this. But with the use of high-energy particles from cosmic rays and particle accelerators and studying the resulting particle tracks, new particles were discovered. So how? Well, 2 ways. We could look at bubble chambers or cloud chambers, and they both actually do almost the same thing. It's just a slightly different setup. So here is C.T.R. Wilson's cloud chamber. Essentially, we've got a vacuum pump, and what happens is we get a supercooled gas, and the gas is cooled to a temperature slightly below its usual condensation point. Means it's supercooled. When a charged particle enters that mixture, they act as a condensation nuclei. So think dust particles in cloud formation, and tiny droplets of mist will form around them. So as those ions travel through the chamber, they leave tiny cloud trails or tracks that then can be photographed and analyzed. So if it's going in a nice straight line, we're going to see a bunch of bubbles going in a straight line. Similar idea with a bubble chamber. This is a little bit later on. D.A. Glasser in 1952 developed the first bubble chamber. It's a bit larger, as you can see. Here we've got liquid that's close to the boiling point, and when we send these ions through it, they leave a trail of bubbles characteristic of boiling point, much like the droplets for a cloud chamber. So same kind of an idea. This is a bit easier to use because we don't need a supercooled gas. All right. Since bubble chambers use liquid, usually liquid hydrogen, which have a greater density of atoms than the cloud chamber, it more efficiently tracks the path and the interactions. So I say hot liquid, hot for the liquid, just below the boiling point. Now for hydrogen, this is definitely still cold, but it is more dense. We get more bubbles that form. We get a better picture. All right. So for example, if we have an alpha emitter and we set it in one of these chambers, we're going to get fairly wide tracks. So it's a broad track because it's relatively large, many collisions with the atoms around it. If I bathe the region in a magnetic field, alpha particle deflects in a manner consistent with right-hand rule number 3 because it is positively charged. So in this case here, again, right-hand rule number 3, my thumb is pointing to the right. My fingers are coming out of the page because that's what my magnetic field is doing, which means the magnetic force is downwards and the alpha particle bends away. And it doesn't deflect very much because it does have a large mass, right? It bends away from being straight across, and there we go. Beta particles are narrower tracks. It's relatively tiny, and it has fewer collisions with the atoms. In terms of the direction of this, well, if we do the same magnetic field, again coming out towards me, now this is a negatively charged particle, so I'm using left-hand rule number 3, and again my thumb is going to the right. My fingers are coming out of the page, which means my palm is facing upwards, and my beta particles are moving and curving upwards. And they curve relatively more, relatively more compared to the alpha particle. Now, a beta positive particle deflects in a manner consistent with right-hand rule number 3, because again, the positron has a positive charge, even though it's got the mass of the electron. So the radius of curvature would be the same, but the direction would be opposite. So this is actually one of the ways that they were first discovered. Since the beta particle and the positron has a smaller mass than an alpha particle, it deflects a lot more in the same magnetic field. Particle tracks tend to move in spirals rather than perfect circles. This is because as they collide with the atoms, they lose energy. So what you can see here is actually this spiral going in both directions, one of them being an alpha not an alpha particle, one of them being a beta particle, and one of them being an anti-proton, an anti-electron or a positron. Right, so same mass, and you can see the spirals are very similar. As it spirals into the center, you get slightly different paths, and that's because as they collide with atoms, that's a little bit of a random process. But initially, anyways, the radius of curvature is exactly the same. The spiral pattern is dependent on exactly when and where it hits atoms and slows down. So we don't get identical spirals because, of course, the distribution of atoms is a little bit random. Photons. They leave no tracks in a cloud chamber because if we have a gamma emitter, those gamma rays don't interact. So if I look at this diagram here, I can see I've got a magnetic field coming out of the page. I've got a wide track here that tells me this is my alpha particle. Now if I start here, a couple things I should know. Number one, this thing that's moving down here, so let's call this track 1, this will be track 2, and this will be track 3. Track 2 has to be positively charged because it is also deflecting the same direction as my alpha particle. It's got to be a lot lighter, so less mass, which means its radius of curvature is smaller. And you can see that 2 and 3 have the same radius of curvature, which means they are identical in everything, mass, speed, to start with anyways, but not charge. Track 2 and track 3 have the opposite charge. And if we know that track 1 is an alpha particle, track 2 has to be our positron, track 3 then is going to be our electron, or beta negative particle and beta positive particle down here for track 2. Also, we've got number 1 here. This, nothing is shown. This could be our photon. Okay, so numbers are slightly different. Particle 1 leaves no track. It's annoying on this diagram. I have to show something. So I've got the dashed line just to show that something was there. Right, I could have a detector over here somewhere to show me that, yes, there was a gamma ray. There's a photon there, but it is undeflected, right? It goes in a straight line and it leaves no track. So this is a photon. Particle 2, negatively charged, narrow track, it's a beta particle. Deflects in a manner consistent with left-hand rule number 3. And again, we looked at this already. But left-hand rule number 3, of course, says I use my thumb on my left hand pointing in the direction of its velocity, and initially there's the line, which means the magnetic force is pushing towards the center of this circle. And Small particle, likely beta negative, so it's an electron. Particle 3, same, we talked about this in a minute, so it's positive. Small particle, likely it's beta positive, so this is a positron. And then track 4, we talked about this already, positive charge, not much deflection, likely an alpha particle. Alright, so two unknown particles enter a magnetic field at the same speed as shown. Here we've got our magnetic field going into the page instead of coming out. Using equations and the principles of physics, compare the two particles. Do not attempt to identify them. So we could suggest, right, I'm going to just say, you're going to want to say, oh, 1 is probably an alpha particle and 2 is a beta particle. Okay, we're going to ignore that. We're just going to say, what can we know about them based only on what we see here? Right? So let's take a look. What can we learn about them? So first we compare them using the hand rule. So for number 1, again, I figure out what is going to cause magnetic force to be going essentially up when I've got my thumb pointing to the right and my fingers going into the page. So I can try that with my left hand, fingers going into the page, thumb going to the right, and I'm going to, wait a minute, that's got my palm facing downwards. So this doesn't work. Let's try the right hand rule. Right hand rule, fingers going into the page, thumb to the right, palm goes up. So this tells me I'm using my right hand rule. Charge on number 1 is positive. All right. Charge on number 2. We can tell it's going to be negative, but let's just one step at a time. Again, left hand rule, fingers going into the page, thumb to the right, palm goes down. FM is downwards. It is actually not in that goofy direction there. It's towards the center of the circle. This is a negatively charged particle. So number 1 is positive, number 2 is negative. Okay, you can look at that step at a time. All right. Now we want to compare them mathematically. So they are both going in circular motion. So in both cases, F net equals mass times acceleration. And it's going to be centripetal acceleration, which means it's going to be v squared over r, which means this is magnetic force. QVB equals mv squared over r. We have seen this equation before. One of the v's cancels. QB equals mv squared over r. We don't know the charge or the mass. We could isolate the charge to mass ratio. And so Q over M is equal to V over BR. We notice, hopefully, that the charge to mass ratio, so this whole thing here, has an inverse relationship with the radius, which means particle 1 has a larger radius, which means therefore it's a smaller charge to mass ratio. And particle 2, oops, coming back here, has a small radius, which means its charge to mass ratio is much larger. So comparing its charge and its mass, particle 2's charge is comparably greater than its mass. All right. And initially when some of these cloud trails were seen, this is all scientists had to go on. They're not going to be like, oh yes, number 1 has to be an alpha particle because this, this, and this, and number 2 has to be a beta particle because of these reasons. All they're finding at this point is they're looking at the data and they're saying, well, I don't know charge of either of these particles just by looking at the picture. I don't know the mass, but I do know that the radius is larger. The speed is the same, and probably that's known. The magnetic field strength is known. So what can I learn about this? Well, because the radii are different, I can learn something about their charge to mass ratio. Right. So that was some of the things that they could do. Now, you also have to think about high energy particles here. If we want to study the interior of the nucleus, scientists need particles that are moving at a very high speed, like near the speed of light. This has been costing in the billions, well, first of all, millions initially, and then now today, billions of dollars. But why do we need these high energy particles? So, initially, when scientists wished to study electrons around an atom, they had to overcome the attraction of electrons to the nucleus. Ionization energies were fairly small, right? And so low energy devices, like in the neighborhood of 10 to 20 electron volts, low energy devices, no problem. This is relatively cheap to study, right? We've got the tool in the lab here that allows us to see the gas discharge tubes and then the diffraction gratings, right? This is something like less than $500, and we've accomplished this. And that's today's money. What about the nucleus itself? So Rutherford, he needed to have our alpha particles that could move fast enough to overcome the electric repulsion of the gold nucleus. So initially, right, he's just watching what happens when they get close to the nucleus and are deflected away. Now, energies were needed in the order of like 10 mega electron volts for this to be accomplished. Happily, this naturally occurred from the alpha decay of polonium. So we knew that polonium samples would give us alpha particles enough, and so let's use those. Perfect. Now, what if I want to know about the neutron itself, or the proton itself, and I want to investigate that by colliding something with it? I have to overcome the strong nuclear force at this point. And this is the largest known force in nature, which means I need a lot of energy. Right? So just a quick little comparison here. Between nucleons, the strong nuclear force is about 100 times greater than the electromagnetic force. Within the nucleons themselves, the strong nuclear force is stronger still. As a result, the energies of the incident particles must sometimes be in the order of giga-electron volts or tera-electron volts. And to get to those high energies, it's not cheap. They have to be, if we're trying to accelerate electrons and protons to this, they got to get very close to the speed of light. That requires lots of energy, it requires specialized equipment, and none of those things are cheap. So initially, the idea is, well, what about cosmic radiation? Right? We get bursts of high energy particles, especially protons that come from the sun. Some of these are like 10 to the 14th mega electron volts. This is a huge amount of energy. But our atmosphere makes it so that most of these high energy protons don't reach the surface of the Earth, which means that we can't really do those experiments, at least not in the early 1930s, at the surface of the Earth. If you've got a lab on the International Space Station, potentially you could do this, but the expense and the difficulty and then the danger to scientists and losing some of your shielding from those high energy protons is not a great way to do this. So negative on that one. So we've got Robert Van de Graaff here. Now his Van de Graaff generators were slightly bigger than the one that we have in our lab. You can see a couple people in this picture here. Same idea, obviously. Now his is again slightly bigger than ours. But he's basically going to be creating a high voltage, 50 kilovolts, strips electrons off the volt, giving the belt itself a significant positive charge. Belt drive moves the positive charge up to the top. This uses a charge comb. Electrons are stripped off the metal pressure dome, giving the dome a positive charge. So this belt is positively charged. It attracts the electrons from the dome. Belt becomes more neutral. The dome becomes positive. And the longer we continue this process, the bigger the positive charge on the dome becomes. Near the top of the pressure dome is an ion source, in this case a source of protons. Protons themselves are repelled from the dome, and they're like charges, so we've got an ion source up here, and they're repelled by all of the positive charges here, so they accelerate downwards. High energy protons smash into the ground and target atoms at the bottom, and then scientists could analyze the resulting subatomic particles using cloud or bubble chambers. Van de Graaff generators or Van de Graaff accelerators, when in tandem, can get particles up to a maximum energy of about 100 mega electron volts. So you could imagine another one of these on the opposite. So imagine a mirror right here. So we've got another one kind of down below the page here. Oops, settle down. No, do not do that. Another one down below the page here. And if we've got these ions accelerating towards each other, we can get lots of energy there. Okay, so essentially we're using static electricity here. So Van de Graaff generators return. All right, so let's try this question. Particle has a charge to mass ratio of that. It is accelerated from rest through a potential difference of 12 kilovolts. We want to know its final speed. So we start looking and say, what do we have that does something with charge and mass and voltage? And I see a formula on my formula sheet. So I see a formula on my formula sheet. Delta voltage is equal to change in energy over Q. And if I think through this a little bit, if I'm looking for speed, and I'm going to ignore the effects of relativity, which is something happily we don't have to do with in Physics 30 now. One of the things I know is that this is going to be kinetic energy in this case here. And if I'm dealing with this as kinetic energy, this is the same as voltage. So delta voltage is equal to 1/2 mv squared divided by Q. I have a charge to mass ratio here. So guess what I can do? I can multiply both sides by Q and divide, that's supposed to be a Q, sorry, divide both sides by M. Now I have delta voltage multiplied by Q over M. That's my charge to mass ratio. So I don't know the charge, I don't know the mass, but I do know the ratio of those two. So this value here goes into this equation here at that spot. So this is equal to, at this point, 1/2 v squared. All right, I need to get v by itself. And so I'm going to multiply both sides by 2. And then I'll eventually square root it. So in the end, I end up with v for velocity is equal to 2 delta v multiplied by Q over M. That's my charge to mass ratio. And then square rooted. And V is going to be equal to, and I can plug numbers in here. Sorry, I gotta move this around. 2 times my voltage. Now my voltage is 12 kilovolts, so this is going to be 12 times 10 to the 3 volts. And then multiply that by my charge to mass ratio of 3.9 times 10 to the 10, it is 10th. 10 to the 10th coulombs per kilogram. And then I take the square root of all of this. So when I plug this into my calculator, 2 times 12 times 10 to the third times 3.9 times 10 to the 10th. And then square root that answer, I end up with... Nope, I don't end up with that. Let's try again. I ended up hitting square root twice, so that's a problem. There we go. 3.06, well, it's 3.0594 and so on, but 3.06, and actually that rounds to 3.1 times 10 to the 7th. So it's roughly 10% the speed of light. So this is moving along rather quickly. All right. So continuing here, we can then, this is step by step what we did. We just used conservation of energy, right? So the initial energy is this electric potential energy, and the final energy is going to be kinetic energy. Initial potential energy, final kinetic. There we go, there we go. Doing all the work to get the charge to mass ratio to be there. So, right, I'm isolating the charge to mass ratio, and we can then multiply that by 2 times the voltage, and this is exactly what we did. It's kind of a step-by-step process here, though. All right, then we need to talk about a cyclotron. First developed in 1930 by Ernest Lawrence. Essentially, we have an electromagnet with its north pole facing down and a south pole here, a D-shaped cavity, and we're going to have accelerated particles going in bigger and bigger circles and eventually come shooting out of this thing. Protons generally are released from a source in the midway point between the two Ds. You can see this is sort of a D shape. This is a mirror image D shape. We have an AC power source, which means that the current in these electromagnets keeps reversing, which helps everything to accelerate. Initial voltage from the AC source creates an electric field towards the right from positive to negative, which means our positive protons accelerate this way. And we've got a magnet here, a magnetic field here, so it flips it around, comes back this way. By the time it makes it back to here, our AC source has flipped, and now we have negative on this side and positive on this side. So it's attracted over here, and it speeds up. And it comes around to here. By then it's flipped again. Now this side is negative again on the right, so it's attracted and it speeds up again. It goes around here. Now you can see the radius is getting bigger because the speed is getting bigger. By the time it gets to here, we have positive on the left, on the right, and negative on the left. So it accelerates over to here again. And then around, it's going faster now. The AC source has flipped again. Now we've got negative over here, so it accelerates towards the negative. And it speeds up some more. Our speed gets bigger, our radius gets bigger. Accelerate, now it's flipped, accelerates this way. Everything speeds up, and finally it goes firing out here. And away we go. Now we've got a fairly high speed moving particle. We should talk about what the direction of the magnetic field is. So this is a positively charged particle. Initially, it's moving this direction, or to the right. So I've got a positively charged particle. This is going to be my right-hand rule. And I got to figure out which way is going to result in a magnetic force going up. So my thumb is pointing the direction that the proton is initially moving, which is to the right. I want my magnetic force to go towards the top of the page to make it curve that way, which means my fingers have to go into the page. So our magnetic field is into the page here, right? If I did the right button, that would help too. Right-hand rule number 3, Q is positive, away we go, B goes into the page, and that's the same on both sides actually. Alright, moving along. Proton moves in uniform circular motion. It leaves here with the same speed that it enters, but now, this is what I was saying originally, if the voltage didn't change, so if the AC source was not AC, by the time it got back to the middle here, it's back down to rest. Because it's actually moving against the electric source, against the electric field now. But if we have an AC current, we set up the timing just right so that it flip-flops, and then, like I said before, it accelerates from here over to here. Circular motion, directed back this way, accelerates again. Speed gets bigger every time it goes through the magnetic, or through the electric field. Okay. Could you show mathematically why it should why it would have a larger radius? And if you think about this, well, there's a few ways you could go about doing this, but one of them is going to say, well, what's the force acting on it in the magnetic field region? Well, in the magnetic field region, there's one force acting on this thing, and that is the magnetic force. But F net is equal to mass times acceleration. Again, this is in the magnetic field region. And in that magnetic field region, it's moving in circular motion, so it's mass times the centripetal acceleration, which means I've got QVB is equal to mv squared over r. And simplifying a little bit, I'm left with QB equals mv over r. And if I solve for r, r is going to be equal to mv over qb. And what this tells me is that the radius is directly proportional to velocity. So as the radius increases, the velocity increases. Or I could look at it, flip it around the other way. Velocity is directly proportional to radius. Right, so here's the derivation, kind of step by step. Lovely. Since the proton enters at a higher speed, the radius also will be larger. And continuing on through what I said, each cycle through the cyclotron is going to speed it up some more. And our AC source, right, the frequency of revolution, is the same because even though it moves a short distance here, it's moving at a low speed. Longer distance here, it's moving at a higher speed. Still longer distance here, the time for each of these little semicircles that I've drawn is exactly the same. And that time is the same simply because the speed is increasing every time. When it reaches its maximum radius, at least for this magnetic field, it exits the cyclotron, and now we can smack it into something and analyze the resulting collisions with a cloud or a bubble chamber. Cyclotrons, we get up to a maximum of about 700 mega electron volts. Maximum energy of the proton is determined by the strength of the magnetic field. And the closer the proton gets to the speed of light, the more relativity is going to play a role. Which means that the mass of the proton, or at least the relativistic mass, increases significantly, which actually also changes its frequency of revolution. And it's difficult for this device to adjust for the effects of relativity. So if we go back to our equations, oh, there we are. If mass is, so as radius increases, speed increases. But the problem is, because of relativity, as speed increases, so does mass. And now radius is dependent on both mass and velocity. So we get to a maximum velocity where mass starts to really increase, at least relativistic mass increases. We run into problems. And that's why we max out in terms of our maximum energy that proton can get. So if a cyclotron has a maximum diameter of 40 centimeters, and a proton exits the cyclotron with a maximum kinetic energy of 7 mega electron volts, determine the magnetic field inside of the Ds. Right, so we look at this and we say, okay, what's going on here? And make myself a bit more room. Try this on your own. It's essentially the same formula we were just looking at. We're saying, okay, well, Fm equals MAC. We know maximum kinetic energy, so let's we can use that kinetic energy eventually to get to V, right? But QVB is equal to mv squared over r. We're going to have to change this mega electron volts into joules. And we need to change our 40 centimeters here into meters. So maximum diameter of 40 centimeters, which means our radius is going to be 0. That's a terrible 0. Let's try again. 0.200 meters. All right. Maximum kinetic energy is 7 mega electron volts. Let's change that into joules. So 7.00 mega electron volts. We got to change it just to electron volts. So that's times 10 to the 6 electron volts. And we are going to multiply this by our conversion factor, where we have joules on the top and electron volts on the bottom. And we basically have 1.60, got it right this time, times 10 to the negative 19 joule, negative 9, I'm too close to the top of the screen, 19 joules per 1 electron volt. So 7 times 10 to the 6th times 1.6 times 10 to the negative 19. And this means our kinetic energy of these protons is equal to 1.12 times 10 to the negative 12 joules. And this is equal to, of course, 1/2 mv squared. So if EK equals 1/2 mv squared, from my data sheet I know the mass of a proton, so 2 EK divided by m, and square rooted is going to give me the velocity. All right, so I multiplied both sides by 2 and divided both sides by m. And that's going to get rid of my 1/2. And it gets rid of my mass. I'm left with v squared. I take the square root and away we go. So figuring this out, v is equal to 2 times ek, which is 1.12 times 10 to the negative 12 joules divided by the mass of my proton, which is going to be 1.67 times 10 to the negative 27. That's on your data sheet. And that is kilograms. And then I'm going to square root all of this. And I'm left with a speed of 3.66 and so on. I don't want to round yet, so I'll leave the unrounded value in my calculator. 3.66 and more, 3.6623999985 times 10 to the 7 meters per second. I can go back now to this, and I'm going to solve for B. I know Q, I know V, I know M, I know R. I can solve for B. So I get rid of my velocity on this side, divide both sides by V, gets rid of the squared there. I'm going to divide both sides by Q. And B, oops, is then equal to MV over QR. B is going to be my mass of my proton, 1.67 times 10 to the negative 27. And that is, of course, measured in kilograms. I'm running out of space in a big way. Times my radius of, good thing I'm writing in blue, 0.2 meters. 3 significant digits, but I'm just saving space. Divided by my elementary charge, 1.60 times 10 to the negative 19. Coulombs. And the radius is 0. Nope. Oh, good grief. Did I do that for real? I did that for real. So I saw in my question that there was an R, and I put it on the top instead of on the bottom. So this value here I have to throw into here, and I just run out of room, so I'm drawing my arrow. And my radius down here is 0.2 meters. Lovely. Now magnetic field is measured in Teslas, So we can do this real quickly. 1.67 times 10 to the negative 27 times my speed, which is still in my calculator, so that's 3.6623999985, and so on, times 10 to the 7th. Divide that by my elementary charge, 1.6 times 10 to the negative 19. Divide that by 0.2. And I end up here needing a 1.91131, so on. 3 significant digits, 1.91 Tesla electromagnet. All right, so step by step, here we go. And final answer, lovely. Proton enters the gap with a speed of 4.2 times 10 to the 6 meters per second. Potential difference across the gap is 100 kilovolts. So at this point in time, we are looking for change in kinetic energy, right? So basically, I'm using my formula, delta V equals delta E over Q, which means Q delta V. So Q, the charge, times my voltage is going to equal my change in kinetic energy. All right, so if I have an initial speed, my change in kinetic energy, I'm going to find out, I want to find out how much does the speed change, right? So QV is equal to 1/2 mv squared. And really this is going to be the change in velocity squared. So whatever v I get here as my answer, I'm going to add to this. Because I have that to start with, all this formula gets me is the change in kinetic energy. So Q, elementary charge, V, this is my delta V, this is my voltage, 100 kilovolts, 100 times 10 to the 3 volts. Okay, so that's where we get that from. Mass, this is the mass of the proton. This is off our data sheet. And then we're going to find V squared. It's tricky because it has a speed here. That's not our final answer. We find this V and add it to this one because it's gaining that much speed, because it's gaining this much kinetic energy. All right. We can go conservation of energy. So this is essentially doing the same thing mathematically that I was saying in words. It's just that it's doing it a little bit more nicely. Right, so EKF is going to look at the potential energy initially. That's the energy it's gaining from this electric field, plus the initial kinetic energy. So half mv squared, mv initial squared, that's that 4.2 times 10 to the 6 meters per second. Right, mass is the mass of the proton. V initial is there. Q is here, and my voltage is here. Now this tells me its final kinetic energy is going to be that many joules. I need now to convert that into speed, and here we go. So we started at 4.2 times 10 to the 6 meters per second. It's gone up to 6.1 times 10 to the 6 meters per second. All right, so a linear accelerator, our LINAC, was first developed by Rolf Witherow in 1928. Basic design is we've got these, we call them drift tubes. We have an ion source, radio frequency oscillators, all kinds of fun stuff going on. As it goes through each of these tubes, it's going to go at a constant speed through it. What happens next? Well, between the drift tubes are electric fields, which cause the electron to accelerate. Right? So the electron is attracted to the positive end, it accelerates. Beautiful. Reaches the next tube and travels through it at a constant speed. Another gap, another electric field. Transfer of electric field occurs at a constant rate or a constant frequency. Reaches the next drift tube at an even higher speed. Why are these drift tubes getting longer? It's because the transfer of electric fields from gap to gaps happens at a regular frequency, right? But the electron is traveling faster. So here it's moving pretty slow. We have a short drift tube. Speed it up, longer drift tube, because the time it takes to go from here to here is the same as the time to go from here to here, which is the same as this time to go from there to there. So we want to reach the gaps at the same time intervals. The drift tubes have to be longer. By the time it reaches the target, it can have an energy of 50 gigaelectron volts or more. Smash into the target, subatomic particles are analyzed. Some linear accelerators can be very short and used in devices such as in medicine. So external beam therapy, we could use this, something like this, for potentially a source of radiation therapy. Others, for like particle physics, can be kilometers long. The Stanford Linear Accelerator, you can see it here. Imagine that that's a straight line. Goes even under a highway. It is very long. And then we have a synchrotron. L.W. Alvarez developed this idea in the 1950s. And the basic design here is we've got an accelerating cavity, and then we've got a bunch of deflecting magnets which keeps it moving in a circle, and then various places along the way where particles can be extracted to smack into other stuff. Otherwise, we just keep accelerating them as it goes around in our circle. In a cyclotron, the radius increases as the speed increases. In a synchrotron, the particles move in a circle of a fixed radius. So how does this work? Well, we first inject them into the synchrotron, which is an evacuated, like a vacuum tube that is shaped in a fixed circle. Protons are sped up through an electric field. That's in the accelerating cavity. Path of the protons is bent into circular motion using magnets that are spaced periodically throughout the synchrotron. In between each magnet, we've got electric fields which speed it up, similar to a linear accelerator. So the proton speeds up many times every lap. As the speed and mass of the particles increase, the speed of the deflecting magnets increase as well. So as we increase the speed, we just have magnets that get stronger and stronger and stronger and stronger. Eventually, the protons reach their maximum speed as high as like 0.9999, lots of nines at C, which is like 99.9999% of the speed of light. At which point they are extracted or directed out, and at that point they've got 500 gigaelectron volts of energy or even more. Smack them at target atoms. Resulting subatomic particles are analyzed using cloud or bubble chambers. X-rays are being constantly emitted because the protons are accelerating. So this is called synchrotron radiation, these X-rays. Which means obviously you probably don't want to stand right outside of it. Rather than simply losing the X-ray energy as waste, research stations are placed around the synchrotron. They use these high-frequency X-rays for a variety of other experiments, which is sort of a useful way to use them. Synchrotrons are very large and usually underground. Some can be many kilometers in diameter. The Fermi National Accelerator Laboratory in the States, you can see this is an overhead view. It's big. CERN on the border between Switzerland and France, much bigger, 27 or 20 something kilometer diameter, I believe. So to increase the colliding energies even more, scientists have developed colliding beams. This is where they generate two beams of these high energy particles with linear or circular accelerators and smash them into each other. When this was written anyways, the highest energy of impact was like 900 giga electron volts. And so we've got a linear collider here, and you can see, I mean, basically we've got two trains that go this way, and at this point here they get split and then smack into each other right here. Much more about this. This is kind of the background for what we need to do on Monday. Thanks.